Okay, so today we start so-called electrical and mechanical vibrations. Last time I made a presentation and we showed some examples of, an example of mechanical vibration. Actually, that is something more complicated than the ones we will consider today. That's actually related to wave equation, maybe, but basically they are the same. Same characteristics. We will talk about that. Okay, so first I will mention the example we studied previously. Electrical vibrations. Suppose we have a circuit like this, RLC circuit. R is the resistance, C is the capacitor, and L is the inductor, and ET is the external potential applied to the circuit. Let QT denote the amount of charge in the capacitor C. Okay. C. And the potential difference at the ends of this circuit is how much? It is okay. It is Q over C. The potential difference at the ends of the resistance is how much? It is I times R, and the potential difference at the ends of the inductor is what? L times I derivative. Here I is just the capacitor, sorry, the current. IT current current is the same at all points, right? Current at time t, and we know that current is nothing but actually time derivative of the charge. Okay, so it is Q prime. Therefore this equation which can be written like this, so L times I prime plus I times R plus Q over C is equal to, so total potential is just ET, or this is just L Y double prime plus R times Y prime plus 1 over C times Y equals ET, where Y is just QT. Okay, if Y represents the charge, then this is the differential equation which describes how the charge in the capacitor C changes in time. And today we will consider this equation. Basically, this is electrical vibration. What about mechanical vibration? Of course, there's there are lots of different types of mechanical vibration. This is one example. Okay, suppose we have a system like this, and we have some mass here, and we have a spring, and we apply also some force to the spring. Okay, now suppose ut is uh, the amount of displacement from the rest position. Okay, in other words, the spring is not stretched or squeezed. Okay, it's in relaxed position, uh, and ut is the amount of displacement from that position. Okay, it can be positive or negative. Let's say this is the positive direction and this is the negative direction uh, for ut. Okay, now let's write down the forces acting on M. Well, here is my mass M. There is, of course, the force acted on this mass by the spring. How much? Well, it is just the amount of displacement times the spring constant. So K is the spring constant. And it is in the, of course, negative direction. So for U, this is the positive direction. The force acted by the spring is in the other direction. So let me say this is minus Ku. And then I have this force, external force I am applying, Ft, external force we apply to the system. And there is also okay, resistance or uh, yeah, resistance. So let's say okay, so it is gamma times u prime. So this is the resistance uh, due to uh, okay resistance applied to the object uh, by the well, let's say table, and it is proportional to the velocity. So if the object is not moving, then there is no force applied. Actually, the okay, maybe we should say this is not the so this is maybe not resistance, but like drag force. Okay, let me say drag force. So it moves inside some, let's say maybe liquid or well, it can be also the air. And suppose there is a force applied to the object proportional to the velocity of the object. You may also consider something like this. Okay, so this object is here and this is a bucket full of water or some other liquid, and it just goes up and down inside this. Maybe this is more realistic picture. And there is this force applied to the object which is proportional to the velocity of the object. Okay. So what is the total force then applied to the object? So this is also in the negative direction. So if the object is moving this way, then drag force is in the opposite direction. So that's why we put minus sign here. Okay. So total force applied to the object, the mass, is how much? So it is F of t minus Ku minus gamma u prime. And from Newton's law of motion, second law of motion, we know that this total force is equal to m times the acceleration, at. In this case, it is nothing but the second derivative of u is the acceleration. At time t. So what we have is then total force is equal to the acceleration. So m times u double prime is equal to ft minus ku minus gamma u prime, and therefore we have this m double prime plus gamma u prime plus ku equals f of t. So that's the equation we obtained. Note that this equation is the same as uh, the equation we have here, right? Same equation, only the constants have different names. So, you know, as a mathematical model, mechanical vibrations and electrical vibrations are the same. So if you understand one of them, you understand all of them. Okay, now let's see how different types of situations gives us different solutions. First one is so-called undamped free vibrations. Undamped means either in electrical vibrations, means the resistance is zero. Mechanical vibrations, gamma is zero. So the coefficient of the first derivative term is zero. So our maybe mechanically this is something like this. We have spring. Okay, we have spring, and mass is just moving up and down, and there is no uh, external force acting on this object. Okay, there is no air resistance or anything. Okay, and there is no external force, only gravity. But you may also ignore gravity, because gravity, what it does, it just pulls down the object a little bit more and then it stops. So here there is no external force. We may consider it this way. So our equation is then this. So K times U equals 0. So here free vibration means no external force. No external force. And this means f of t is 0. Okay. So in this equation, let this guy to be 0 and gamma term is 0. So I have just mu double prime plus ku equals 0. Okay, so we have only this equation. And here, of course, all these coefficients are positive numbers, right? So k is a positive number. How can we solve this? Well, this is a constant coefficient second order homogeneous equation. We write down its characteristic equation, which is just mr squared plus k equals 0, right? I replace u terms by the powers of r, the power of r being the order of the derivative of the u term. Second derivative r to the power 2, zeroth derivative r to the power 0, which is just 1. And then from this we obtain the roots. Here roots are just plus minus square root of minus k over m. K is the spring constant, which is a positive number. M is the mass of the object, which is again positive. So inside the parenthesis is a negative number. Therefore, this is plus minus I times omega 0, where omega 0 is a positive real number, with omega squared is equal to k over m. Okay, so it is just the square root of k over m. Ya da şöyle diyeyim, omega 0 is k over m, which is a positive number. Okay, this omega 0 is called natural frequency of the system. Note that in this case, of course, what is this? This is just the general solution, C1 times cosine omega 0 t plus C2 times sine omega 0 t, right? And omega 0 t is called the natural frequency of the system. Okay, so ut is equal to C1 times cosine omega 0 t plus C2 times sine omega 0 t. Okay, now if we were given some initial conditions, let's say, okay, suppose, so this is the general solution. Assume that we are given initial conditions like u of t, u of 0, let's say, equals u0, and u prime 0 is just u prime u0 prime. This means what? The initial position of the object, okay, from or initial displacement from the equilibrium position is u0, and initial velocity. So the object may have an initial velocity at the beginning. Okay. For once you have this initial conditions, plugging them, you will get C1 and C2. Let's say C1 is just A and C2 is B. So our equation becomes what? A times cosine omega 0t plus B times sine omega 0t. Okay, so for some real numbers A and B, right? We know that any initial value problem has a unique solution. So once we are given initial conditions, I can determine C1 and C2 from the general solution and obtain the unique solution. All right. Now there is a nice way of representing such an expression. You will probably remember from high school. What's that? Okay, now let R to be a squared, b squared, and then square root, and write ut as follows: a over r. So okay, r times a over r times cosine omega 0t plus b over r times sine omega 0t. Here you see a over r squared plus b over r squared is equal to 1. So a over r and b over r is a point on the circle, right? So a over r, I'm sorry, and b over r is a point on the circle. And actually, if I draw this line segment and call this angle, let's say delta, then of course a over r is just cosine delta and b over r is just sine delta. So my ut is then just r times cosine omega 0t cosine delta plus sine omega 0t sine delta, and we know that this is just cosine omega 0t minus delta. So this means what? This means I can, picture this. Okay, let me just do it here. So R is, let's say, is this one, and minus R is here. I have a sine, cosine wave. Not sine, cosine, and something like this. Okay, it goes like this. Yes, so the distance between this point and this point, so whatever it is, so what is this distance? Is the so this thing is just a full cycle, right? Or maybe let me do it from here. So what is the difference here? So this should correspond to 2 pi in cosine, but here I multiply t by omega 0. So this distance is just 2 pi over omega 0. Okay, omega 0. So this is the uh, wavelength. Okay, 2 pi over omega 0 wavelength. Omega 0 is called, we said it's the natural frequency, right? Yeah. Omega 0 is the natural frequency, and R is the amplitude of the wave. Amplitude of the wave. Okay. So this is undamped free vibration. Okay. And this gamma is called phase. So it is a shift from so gamma is this, I guess. Yeah. So gamma is this p. Gamma is this length. Okay. Shift phase or shift. Okay. So here is one example. Let's say we have this equation which corresponds to K equals 10 kilogram no, not 10, 60. Let's say kilogram per centimeter. Yes. And mass is 10 over 32 kilogram second squared over centimeter. Then this is the equation. So m double prime plus ku. Okay. The equation, and let's say so okay, assume u0 equals 1 over 6 centimeter, and u0 prime is minus 1 centimeter per second. So it means the initial position of the spring is 1 over 6 centimeters. So it is just stretched this much, 1 over 6 centimeters. And its initial velocity is minus 1. So it means we gave this spring a negative velocity. So let's say if this is the spring, this is, let's say, the position where no stretched, the amount of stretch is 0. So here in our case, the object is here, so this is the amount of stretch, so u0, which is 1 over 6, and the mass has negative velocity. If I take this is the positive direction, this is the negative direction, so it means initially this has negative velocity, so minus 1 centimeter per second. Okay, so I pull it down, I pull the object down and throw it upward, okay, with this much velocity. And then if you solve this equation, you will get C1 times cosine omega 0 t sine C2 times sine omega 0 t. Omega 0 becomes just square root of what was this? Square root of k over m. So it is just 60 divided by sorry 10 over 32. So I have this. So it is 6 times 32. So 4 goes evet. Evet. Ya aslında kitapta orada pound oluyor. Pound acaba şey mi? Force herhalde. Sandır kilogram yazayım ben şuraya. Tabii o zaman bu yani kitabı değiştireyim dedim ama belki orada hata yaptım. Şöyle diyeyim o zaman burası pound bölü feet aslında. Öyle yazayım. Bu da mass pound s kare feet. Bu da feet. Bu da feet per second. Evet, tamam. Şimdi bu ifade ne olacak o zaman? 6 çarpı 32 2 üzeri 5, 2 üzeri 6, 8 dışarı çıkacak. 8 çarpı karekök 3. O zaman bu C1 cosine 8 times square root of 3 sine 8 times square root of 3t. And if you plug the initial conditions, you get plug the initial conditions to get A equals 1 over 6 and B is minus 1 over 8 square root of 3. So U is just 1 over 6 times cosine 8 root 3 t, and this is 1 over 8 1 1 over 8 root 3 times sine 8 root 3 t. And actually, if you just compute r, the amplitude, so it is just 1 over 6 times, so a squared plus b squared, isterseniz şöyle yazayım, a squared plus b squared and then square root, so it is 1 over 36 plus 1 over 192 square root, bu da 0.18162 gibi bir şey çıkıyormuş. Buradan şunu hesaplarsanız bu da şimdi şeydi, r a times cosine delta, b is r times sine delta. From this we get tangent delta is equal to b over a, b over a, b over a. Therefore, delta is just tangent inverse b over a. Okay. Yes. And that is just minus approximately 0.40864 radian. And solution is something like this. Okay, so 0.18 minus 0.18, so it's r basically, and ya da şöyle diyeyim, 0.2 olsun, bu da eksi 0.2. Bizimkinin genliği biraz düşük değil mi? Tam o kadar değil. İşte şöyle bir şey. Okay. Peki. Burada dalga boyu işte ona t deniyor. O da 0.453. Okay. Wavelength. Okay. The next one is damped free vibration. So this time external force is 0, but gamma is not 0. Okay, so there is damping. So this is like, you have a spring and again a mass, and it goes up and down. And let's say we have a bucket and we have some water in it, and this mass is just moving up and down inside the bucket. The equation is this: f of t, but it is just 0. Well, how can we solve this? Again, we write down characteristic equation, so mr squared plus gamma r plus k equals 0. And from this, we have two roots, r1 and 2. They are just gamma minus gamma plus minus gamma squared minus 4 mk divided by 2m. All right. Now, depending on these constants, we will have three cases, right? So the roots can be real numbers, imaginary complex numbers, in other words, non-real numbers, or the roots may coincide. Okay, so I may have a double root. So we have to consider all of this separately. Okay, so first one is okay. Uh, we have three cases. Case one, uh, well, okay. Yeah, okay. So case one, this thing is positive. We call this overdamped. So it means gamma is big, okay? Damping factor is big, and gamma squared is greater than 4 times the mass times the spring constant. In other words, the liquid here exerts a lot of force on the moving object, so that the drag force is bigger than uh, you know uh, this gadget, so that the roots are all real. In this case, we have two real roots. So R1 and R2 will be what? Minus gamma, right? Minus gamma uh, plus minus. Okay, so this is plus, let's say, over 2m. Well, this is a positive number, but it is less than certainly gamma squared. Therefore, its square root is less than gamma, and I subtract gamma. Therefore, this is a negative number in total. And R2 is even more negative because this time I subtract. So both roots are negative, okay? And in this case, ut will be what? C1 times e to the power R1t, C2 times e to the power R2t. And both of them are negative numbers, And uh, if you have, say, let's say initial conditions, okay, u0 equals u0, u prime 0 equals u prime 0. Depending on these initial conditions, you will have something like this. Since both of them are negative, either you will have something like this. Let me say a solution like this, or you may have a solution like this. For example, this one corresponds to, let me write it down. This one corresponds to the following initial conditions. u0 equals 1 over 2 and u prime 0 equals 7 over 4. And this one is u0 equals 1 over 2 again. It starts from the same position, but the velocity is this time negative. So minus 7 over 4. So this means what? You pull the object down, and in one of them you push it upward, and in the other one you push it downward. So if you push it upward, then the object is moving a little bit high above, and then it just okay, actually my, I guess, direction, this was plus, this was minus. So in this case, negative velocity means I push it upward, so object goes a little bit above, and then it just comes down to the rest position. And if I push it downward with positive velocity, it will go down and then come back to the rest position. There are no oscillations. Okay, the object will move to the equilibrium position, rest position, real quickly because of this exponential terms. Okay. All right, so this is the picture. The second case is case 2. This square, I mean, gamma squared minus 4mk is 0. In this case, R1 and 2 are both of them equal to the same number, gamma over minus gamma over 2m, right? Because square root term is 0. So what are the solutions? One of them is, so ut is just c1 times e to the power, let me call this number r, rt. And what about the second solution? Well, since the root is repeated, so it is c2 times t times e to the power rt. But okay, so this is in the, okay, let me write it this way. So this is and suppose again we have initial conditions. So we have a times, okay, minus gamma over 2m minus gamma t over 2m, and then a times a plus bt. Okay, yeah, minus gamma t over 2m is the common factor. I take it outside, and then I have a linear term like this, a plus bt. You see, although this gadget, as t increases, goes to plus or minus infinity depending on the sign of b, this exponential terms goes very rapidly to 0. Therefore, this expression will go to 0 as t goes to infinity. Okay, so it means what? Our system, because of the damping, okay, it loses its energy. There are no external force applied to the system. Therefore, the object will go up and down, but it will lose its energy and it will come to the equilibrium position and stop there. And how the solution looks like? Well, it is actually similar to above one. Although we have this t term here, it won't cause much actually difference in the shape. So it will, again, it will be something like this. Yani atıyorum şimdi ama again it will be something like this. Okay. Because of this, it may go maybe a little bit more upward, but eventually this term will beat that out and makes the function very small, and it will go to 0 as t increases. Okay, let me stop here. In the second hour, I'll consider the third case, so case 3, underdamped vibration. Okay, this is called critical damped, critically damped. Why critically? Because this discriminant is 0, so it's a kind of critical position, and we will see why it is called actually critical, because once you pass that critical solution, things will change dramatically. Okay, let me stop here and I'll continue the next hour.